Okay? So one of the first things I want to talk about today is a little bit more about the thermodynamics of electrochemical cells and electrochemical systems. So what have we learned about thermodynamics already? You guys tell me any of the equations or concepts we learned about? Nernst equation. We'll get to, we know where the Nernst equation came from. I'm not going to derive it again, right? It comes from delta G equals RT ln Q, right? It was free energy. So I want you to consider this chem cell. Now let's think about it. So this AgCl, Cl minus, zinc 2 plus, zinc, right? So this, as written, represents an oxidation going from Ag, right, to AgCl, and this occurs at the anode. If I read this from left to right, and this represents a reduction, and this happens at the cathode. Again, if I read this from left to right. What are the slashes?
Phase boundaries.
Phase boundaries, okay. So what phases do I have here? So I have the solid phase, which is going to be the silver and the zinc. And then I have, in this case, this is an aqueous phase, right? Okay. What is this half reaction represented? What is that half reaction represented? Anything you guys know about, or learned about, or done in lab? Those are reference electrons, silver superchloride reference electron.
You're right.
So this half reaction, this half reaction is just AgCl reference. So this is a cell you could build in lab, right? You could take your reference electrode, you could put a little zinc 2 plus in there, and you could put a zinc wire in there. And you could measure this potential in lab very, very easily. In fact, you've probably done something similar in general chemistry, right? In the laboratory, I suspect. So what is the balanced chemical equation that corresponds to this reaction? So what is the chemical reaction that corresponds to this cell if the forward direction is kind of read left to right? This is the anode, this is the cathode. What's the reaction? Can anybody guess? Make a hypothesis? Doesn't have to be right. Just give me your best guess.
Ag plus zinc chloride yields silver chloride.
Okay. Let's make them associated just to make it a little easier for us. Okay. Goes to what?
Silver chloride.
To AgCl plus what?
Zinc.
Zinc. Okay. So I need to balance this. We'll look and balance that. We can do that. Okay. So that's the reaction that we're interested in, right? It's the 2-electron reduction of zinc. In this case, driven by silver, or measured versus a silver chloride half reaction. What is the cell potential? Like you measure in general chemistry. You guys remember how to do this? E cathode minus E anode. And that, it turns out, what that means is it's E right minus E left. And so if you have a table of standard reduction potentials, so these are standard reduction potentials, you can calculate a cell potential based on the standard reduction potentials. And we'll get into more detail about this, but basically what you're saying is I'm driving this reaction forward, the cathode reaction, versus some reference, and I'm driving the reduction reaction that is actually happening at the anode. It's actually, we're driving it backwards versus that same reference. The reference, since both cancel out, and you're just left with the difference between these equals the cell potential, and I'll show you how that works. So we write a electrochemical cell schematic with these slashes, the different phases. We always put the cathode on the right,
Okay.
So you basically, that's right. This is basically equivalent. And Barnard will talk about that in a confusing way. Cathode's on the right, you take the right minus the left, so this half reaction minus that half reaction, or you cathode minus the anode, it's all the same thing.
Okay.
And we can see that from the thermodynamics really easily. Let's just write it out. At the cathode, let's just go through this example. We have zinc 2 plus 2 electrons going to zinc solid, right? Zinc 2 plus, getting the 2 electrons from silver, going to zinc solid, right? And we can look that up. E naught equals negative 0.76 versus NHE. What's NHE again? The normal hydrogen electrode, the standard hydrogen electrode, they're related, but they're basically, this reversible equilibrium with protons and hydrogen. And our anode reaction, what's our anode reaction? So let's write it as a reduction. We're going to multiply the reduction by -1 times AgCl, the charge, plus an electron goes to Ag plus Cl minus, right? And this is a this is an E naught reduction potential. All I'm writing are reduction potentials. This is a reduction potential. This is a reduction potential too. 0.22 volts versus NHE. For this reduction reaction, this is the half cell reduction potential. We don't write oxidation potential. Even if you're driving an oxidation, that oxidation process is characterized by its standard reduction potential. That's just a bookkeeping mechanism, okay? So when people tell you the oxidation potential of something is something, that's actually kind of a misnomer, and it's confusing what exactly they mean. Because often they actually mean that's the reduction potential, but they're driving an oxidation. So there's a lot of confusion around the terminology because people use it pretty loosely. So anyway, so we're talking about the reduction potentials. So if I add these two things together, right, I get the overall reaction. 2Cl minus plus zinc 2 plus goes to zinc metal plus silver metal plus Cl minus 2 Ag plus, sorry, and 2Cl minus. And actually, I should just write this already. 2 AgCl because it precipitates and forms an insoluble complex. So we should write it as a dissociated ion jet, right? So what's the standard potential of this? Well, what's the cathode? Okay, and minus this reduction potential. So you notice how I multiply this by negative, right? And that's why this becomes minus. So if I take E cell equals negative 0.76 minus 0.22 volts, that equals negative 0.98 volts. What's this versus? It's not versus NHE. Why is it not versus NHE? It's the cell potential. It's like if I have a battery and it measures 9 volts. Like, that's this battery potential. That's not referenced to anything because it's literally this half reaction versus this half reaction. Now, I could say, it's 0.98 volts versus silver chloride. But that would be describing this half reaction. Negative 0.98 versus silver chloride. Right? But it wouldn't be describing the cell potential. Cell potential is not versus a reference electrode, it's the actual potential coming off that cell. Okay, so first of all, is this a spontaneous reaction? Yes or no? What do you guys think?
No, you have to put.
Okay, delta G equals negative NFE. So if delta G is positive, is the reaction spontaneous? No. E is negative, times a negative is a positive. This reaction is not spontaneous. Another way to think about this is, which is a stronger reducing agent? Silver or zinc? As chemists, zinc is a way stronger reducing agent. Silver is a noble, or in that noble metal group, right? So silver is not. Zinc's a much stronger. It's much more willing to give up its electrons than silver. You put zinc in acid, what happens? Hydrogen bubbles up really fast, right? So you guys know all this chemically, actually. So this is just the sort of formalization of that. Let's be more explicit, where this comes from H2 plus zinc 2 plus goes to zinc plus 2H plus. What reaction is this? What is that? Is this related in any way to what we wrote on the other side of the board? Is this a half reaction? Is this a full reaction? Okay, so this is actually the full chemical reaction that this half reaction is actually referring to, right? Because I wrote versus NHE. So what this really refers to is this full reaction, which has delta G naught equals negative NF E naught. And so it's this E naught that is actually put in that table of standard reduction potentials that's derived from the delta G for this chemical reaction that involves this half reaction, right? This reference half reaction. Okay, and I can similarly write another reference half reaction. Here, I'm going to do it a little different. Negative 1 times H2 plus 2AgCl goes to 2Ag plus 2H plus 2Cl minus. 2Ag plus 2H plus 2Cl minus goes to H2 plus 2AgCl. Okay, so these are the same expressions, right? These are equivalent. That one and that one are equivalent. And this is described by delta G equals negative NF E naught for the reduction reaction, but now I flipped the direction of the equation. I made it, right? This is no longer, right? This is now the oxidation of silver, right? By protons, right? To make hydrogen gas. And so here, if this is the reduction, if this E naught is the reduction potential, I actually need to cancel out that negative sign, right? Because it's for what I wrote would be for this equation, but I have to flip it around, so I have to multiply delta G by that negative sign, right? And so when you think about the overall reaction, if I add these together, I'm not going to do this twice, right? It's A plus B, where I choose either one of these, right? They're the same thing. I get my overall reaction. So 2Ag plus 2Cl minus plus Zinc2 plus goes to the zinc metal plus 2AgCl. What is the delta G for this overall reaction? Right? It's delta G total, call this 1, call this 2, equals delta G1 plus delta G2, right? You guys know that. And so we can calculate that now in terms of these things here, and we get negative NF E naught 1, I'll call this 1 and 2, distinguish, plus NF E naught 2. Now, N and F are the same, right? Both these have 2 electrons implicit in them, right? So the 2 electron redox event with zinc. And here I've written it so it involves 2 protons and 2 silver, so N is 2 for both of them, here and here. And F is various constant. So I can rewrite this as equal to negative NF E1 naught minus E2 naught, right? Where E1 is for the cathode, E2 is for the anode. So that's the exact same equation we got before, right? And this is equal to NF E cell, negative NF E cell. So this simplifies to E cell naught equals E1 naught minus E2 naught, or E cathode minus E anode, which is exactly what you knew from general chemistry, and you might have even gone through this in general chemistry, but you kind of forget these things. So this comes from the equivalency between adding cell potentials and adding free energies. And the key thing about the cell potential is the cell potentials are sort of already normalized for the number of electrons transferred, right, in this relationship between delta G and E. number of electrons transferred are accounted for. So when you calculate a cell potential, you actually don't need to worry about the number of electrons transferred, right? So I could look at an aluminum 3+ plus 3 electrons going to aluminum metal, and then I could go look at the potential of zinc 2+ going to zinc metal, and I could make a cell with them. And I could just look up their half reaction potentials. I don't need to care that one's a 3 electron reduction, one's a 2 electron reduction, and I can still calculate the cell potential, because that's all taken into account in the calculation of the delta G's, and it all falls out of the overall equation. Because when you calculate the overall equation, what you're really doing when you do this is you're calculating delta G total equals delta G1 plus delta G2. They're equivalent. And if you want to get from here to a chemical equation, then you need to know N. For that reaction, you need to be able to write a balanced cell reaction that includes the number of electrons. And you could write, for example, I could write this reaction as a 2 electron reduction, or I could multiply it all by 2, right? Or I can multiply it by 3 or 4. It doesn't matter. I can multiply by any number I want. It doesn't change the cell potential, right? And that's practically what happens. It doesn't matter how I measure it. I always get the same cell potential. But from a chemical's perspective, if I combust twice as much hydrogen, or if I take twice as much hydrogen to react with zinc 2+, it's going to release or absorb twice as much energy. So the free energy terms have to scale with the number of electrons, but the cell potentials don't, because one's a potential and one's an actual energy, right? A potential is the capacity to do work, and energy is sort of how much work can it actually do, right? Like just like an electrostatic potential, like imagine like you're on a hill, right? And we talked about this a little bit. If you're on top of Spencer's Butte and you roll a little smaller rock down, it can do a certain amount of work, right? But if I roll a boulder down, it can do a lot more work. So the size of the rock is kind of like the number of the electrons, or how many, whatever you multiply this by. But the height of the hill is kind of like the cell potential. That's the difference between potentials and energies. Okay, so let's consider another example, a little bit more maybe technologically relevant. CO, what's CO?
Carbon monoxide.
So carbon monoxide plus water, just one water, goes to CO2 plus 2H plus 2 electrons. So first of all, is this an oxidation or reduction? It's an oxidation, right? Electrons are on this side. Is this a full reaction or a half reaction? It's a half reaction, right? The question is, what is E0 for this, right? How do we figure out E0? Well, we can write this as a reduction reaction versus a reference, right? CO2 plus 2 protons plus 2 electrons goes to CO plus H2O. And then I can add my reference half reaction and get a total reaction, which is CO2 plus H2 goes to CO plus H2O, and I could get a delta G0 for this. So if anybody think about how you might calculate a delta G0 for this? So if you didn't have a table of reduction potentials, and I wanted to calculate a reduction potential, say I didn't have a table of reduction potentials, but I had, say, or say my table didn't have CO reduction or CO2 reduction in it, right? The one in your general chemistry textbook probably doesn't. Say you have some arbitrary chemical reaction, and you want, half reaction, you want to know the standard reduction potential. How do you get it? You know how we can calculate this? How do we calculate that usually? If you're in general chemistry, I should calculate that. How would you do it? Okay, so what would I do? I would take delta G, right, of formation for the products minus the sum of the delta G of formation for the reactants. And you can just look these up. So those are tabulated for all sorts of, almost every molecule out there. You can find the free energy of formation. Somebody has done the experiment to either calculate that or measure it experimentally. So for basically any reaction, any half reaction, right, I can calculate a delta G for a full reaction versus a reference, in this case hydrogen, and I can get delta G0. And then if I want to do this, so we do the calculation, and it's negative 137 minus 237 minus negative 394 plus 0 equals 20 kilojoules per mole. By the way, the free energy of formation of elements in their standard state are 0. Okay, that's where the H2 is 0. That's the 0 there. So it's 20 kilojoules per mole. Now, how do I go from this to an E naught for this reaction? Okay, so it's delta G naught over NF, negative NF, right? And what's N here? 2, right? Because I have to use 2 protons, 2 electrons. This is a 2 electron reduction CO2. And so this equals 2, and this ends up equaling negative 0.10 volts versus NHE. So, can hydrogen spontaneously reduce CO2? No. Right? And you can see that here. I mean, delta G is positive, right? But it's not very positive. They're pretty close, actually, to each other. So, in fact, this is actually kind of interesting. There's like a whole very large field of research trying to catalyze this reaction. Because people think that if you could pull CO2 out of the atmosphere or capture it when you burn fuels, if you capture the CO2, you could recycle it by doing electrochemistry on it and making CO or other reduced carbon products that you could use as a fuel or use as a chemical feedstock to make the things we use. So there's a lot of people working on that, but the fundamental challenge is actually that the potential for making hydrogen, for reducing protons, H2, is very similar for that to reduce CO2 to its reduced products. So you have to figure out how to make a catalyst that's selective, has very fast kinetics for making CO reduction products, but slow kinetics for making hydrogen gas. So that's actually a big scientific challenge, and that is illustrated here with this very simple thermodynamics. I'm going to ask you now, but you'll do some homework, how would you calculate E versus oxygen electrode? The oxygen couple, right? The oxygen water couple. And you'll do this in homework. This is an application, is a fuel cell, right? So in a fuel cell, you basically have 2 electrodes. You have a membrane that separates them. And in one electrode, you have O2 coming in, plus 4 protons, plus 4 electrons from the electrode, making 2 H2O. And on the other side, we could have a fuel cell that actually ran on CO. And so if this is getting reduced, the CO must be getting oxidized. So CO going to plus 2 H2O. And I'm going to need 4, so I better take 2 COs because it's a 2 electron process per CO. And hopefully that gives me 2 CO2 plus 4H plus. But it's, and plus 4 electrons. And so this is a fuel cell. This reaction as written is spontaneous. You can calculate the delta G. And the electrons flow this way, and you can do work with those electrons as they flow from here to here. That's the definition of fuel cell. And this can be all sorts of different stuff, and you'll calculate in your homework, like what happens if you use methanol or ethanol as a fuel. There's a lot of interest in using ethanol in a fuel cell. We know how to make hydrogen fuel cells work really well. Why do you think you might want to use ethanol in a fuel cell? It's a liquid, right? It's actually pretty challenging to store hydrogen at high pressure and transfer it and all this. So people would love to have an ethanol fuel cell. The only problem is it would make CO2 just like anything else. So then you'd have to have a way to capture CO2, or you'd have to somehow let it in the atmosphere and capture it elsewhere. But a fuel cell, in principle, can be twice as efficient or more than a combustion engine. So the thermodynamic limits for a fuel cell are much better than the thermodynamic limits for a combustion engine, given the practicalities of temperature delta T's that you can do in an engine cycle, like a Carnot cycle or something like that. Which you won't talk about. Okay, so now let's move on and talk a little bit about the concept of reversibility and a reversible process, a reversible versus irreversible electrochemical process. So what does reversibility mean in the context of thermodynamics to you guys? Okay, so let's do some examples. Let's talk about this. Actually, it's very kind of interesting, deep concept. So the definition does depend on context. So what we're going to talk about here is chemical reversibility to start with, and then we're going to talk about thermodynamic reversibility. So Chemical reversibility, it means reversing current reverses the reaction. So here's an example from Bard. We have PT in contact with H2, in contact with H plus, Cl minus, in contact with silver chloride, silver reference electrode. Which one's the anode and which one's the cathode? So this is cathode, right? And this is anode. So if I apply a current one way, I can make protons, right? And I can turn silver chloride into silver, right? That's the reaction that's going to happen. And if I push current the other way, I can oxidize silver, and I can make hydrogen gas. So I can push it back and forth an infinite number of times. That's chemical reversibility. That's what you do in a battery, right? You push charge back and forth. Ideally, if that battery is perfectly chemically reversible, then you can charge and discharge it an infinite number of times. Of course, it's not. There's always some loss every time you push charge one way and the other way. Hopefully, I'll have a chance to talk about that this term later on. But that's chemical reversibility. But it doesn't tell you what Arden said, is that no energy is lost. Imagine you did this, E not cell. So I'm going to take my voltmeter, and a voltmeter is a measuring instrument that has the ability to measure voltage by passing an infinitesimally small current. It's a high impedance instrument, meaning it doesn't really allow the reaction to pass any current, and we're just going to measure how much potential is there, how much driving force there is for the reaction, right? But it's kind of like, a really strong person at the top of that hill, feeling that rock that's trying to push it down the hill, and kind of feeling how hard he has to push to keep it from falling down. That's what the voltmeter is, okay? It's measuring how hard that hill is rolling that block down, how much the electrons want to go from one side to the other, okay? But it's not going to let much reaction happen. And if you do this, you can look this up, E cathode minus E naught anode, and you will measure 0.22 volts, and that's the potential of the silver chloride reference electrode versus the hydrogen reference electrode. Depending on the conditions you measure it at, that's a standard potential. You actually measured it in lab with saturated chloride, not 1 molar, so you get a little bit different potential. You get 0.197, that's what you should measure, versus hydrogen electrode. I like to always write a big line to think about, like, where am I measuring what versus, and I always put NHE in the middle. And for example, if I have a silver chloride, here's AgCl equals 0.2 approximately versus NHE. If I hook that silver chloride up and you put the ground to the NHE and the positive electrode to this one, if I measure that versus this, I'm going to get 0.2 volts. But then if I have an SCE, a standard calomel electrode, you guys use one of those too in the lab? So what's the potential of the standard calomel electrode? Plus 0.24 volts versus NHE, standard calomel electrode, right? And so if I measure AgCl versus the standard calomel, so I put the black lead to the standard calomel and the red lead to the AgCl, what am I going to measure? About 0.04 volts. Negative, right? Because it's negative of there by 0.04 volt. If I switch the leads around, it'll be positive. So it matters what you're measuring versus what, and which is the reference. So you always ground, take the black lead and put it to the thing you want to reference it to, in this case SCE, and then measure the other electrode relative to that. And then you can figure out what side of it it's on by the sign and the magnitude where it is. So I can put all sorts of E naughts on this diagram if I measure versus the reference electrode. So I have some process that I measure out here. E cell is out here. And I know it versus SCE. What is it versus the standard hydrogen electrode? Plus 0.24. It's what I measured versus SCE plus this additional distance. This is why I actually literally still have to do this. Like I write a line and put the lines on it because I always get the signs messed up if I don't, or there's a chance I will. So I go, okay, so this is what I measured. This line, I want this line. I have to add that distance, right? Very straightforward. So you need to do that in the lab, right? So this is what happens. We get 0.22 volts, right? So every electron, another way to think about this is every electron that's flowing through that voltmeter is passing, so each electron passes one fundamental charge, E, or the charge of a Q, what's called Q times V, energy, to voltmeter, right? There's very little current flowing, so we're not changing anything. We're not changing the concentrations here. They're basically not changing because there's like, a picoamp or a tenth of a picoamp of current flow. Very teeny amount of current, but every electron that flows gives you the charge on the electron times the voltage and energy. It's the definition of electrostatic energy, the charge times the voltage gradient, right? The electron volt, right? But what happens, do you think, if I have a battery, or this is a little battery, and what happens if you short wires together? What do you think happens if you short wires together? Well, you have a reaction, right? H2 plus AgCl. Is the current going to be large or small if I short the wires together? Right? Yeah, the ton of current's going to flow. Ton of current's going to flow. This reaction is going to go, right? Spontaneously go because delta G equals negative NFE, and that's smaller than 0. It's spontaneous. And it turns out you won't get 0.22 volts per electron. Because it turns out some of that free energy that's stored in the system will be consumed in actually pushing the current across these interfaces and actually driving the electrochemical reaction. And so then it's still chemically reversible. We can still drive it backwards if I applied a big voltage to it, right? But it's now going to be done in a way that's thermodynamically irreversible. Because basically the whole cell is going to heat up a lot. Have you ever discharged a battery fast on your laptop or your phone? Remember you had a phone in your pocket, like some app's doing something crazy, it gets really hot? Right? That's because that's a manifestation of pulling current out really fast. And when you do stuff fast, you have to use a really large free energy driving force to make it happen, and that all goes into making heat. So you get less energy. So if you discharge your battery fast, you get much less energy out than if you discharge it slow, because more of it's wasted as heat. So that's thermodynamically irreversible. Let's see here. Let's do another example. Let's look a little bit here. So say I actually have a cell. Draw a classic electrochemistry cell here, an H cell. I have my silver wire. It's coated with silver chloride. I have my platinum, and it has H2 bubbled over it, and there's H plus in the electrolyte, and there's H plus here, right? And there's counter ions and things like that, right, to make charge balance. But it's basically this electrochemical cell. There's going to be Cl minus, I guess, Cl minus counter ions. What's it going to look like if I go on the potentiostat and I collect an IE curve? What's it going to look like? So what if I go with potentiostat and just tell it to measure voltage? Is there any current flowing if I just tell it to measure voltage? Teeny amount, right? You can't see it on this scale. So what voltage would I measure? Right? So that's what actually you would measure. Now what happens if you tell the potentiostat to move off of open circuit? So this we call open circuit potential, OCP, open circuit potential of the cell, or in this case, a little battery. What would be the open circuit? What would be the response of the system if I change the applied voltage? Let's put negative over here and positive over here, so we're going to do IUPAC, and this is oxidation, and this is reduction. I like IUPAC better than Texas convention. So what happens, do you think, if I apply a more positive potential? Imagine this is going to be a platinum working electrode, and this is my voltage, current source, and I go to the silver wire. And so this is a 2 electrode measure, but you can think about this. This would be the working electrode, and this would be the reference electrode. It doesn't matter, but how we drew this equation, right? This is the cathode. We draw it as a reduction reaction. So this, therefore, thermodynamics are corresponding to this in the reduction. So that is happening in the working electrode. Okay, so what would happen if we apply positive potential. So if we apply a positive potential, there should be a positive current flow. Okay, what happens if we apply a negative potential? Or a potential negative of this equilibrium potential, right? So remember, if they're in equilibrium and I raise this level, then what happens? Electrons go the other way. I should get a negative current. Okay, so that's how you actually get, this is a power quadrant for a battery, actually. And you can pull energy out, right? So at open circuit, you can't pull any energy because there's no current. This is called short circuit, right? This is what happens if you literally put a wire between the two of them. You get lots of current, but no energy generated because the metal is shorting the two sides together. They're forcing them to the same potential, right? So they were initially different. You're forcing them the same, and all that free energy is wasted as heat. And somewhere in the middle, you get some power. The direction of the reaction determines if it's electrolytic or galvanic. So if it's galvanic, it's acting like a battery. So this is galvanic. The reaction is going forward, as written, and this is electrolytic. Okay, we're driving it back. There is a such thing as thermodynamic or as chemical irreversibility. Just so you have a full understanding here. Chemical irreversibility, like if you take an aryl halide and you reduce it, you often form an aryl radical plus anion, and these are very unstable, right? It's going to make products that are going to be dependent on the chemistry of the structure of this aryl halide that will couple together, for example. And you can't, once they couple and make carbon-carbon bonds, you can't easily go backward. So that's chemical irreversibility. So now let's go back to thermodynamic reversibility, and let's do it a little more formally. The way I think about this is an infinitesimal change in driving force causes reaction to reverse direction. So it basically means your driving force is really, really small. And if it's thermodynamically reversible, it does not increase the entropy of the surroundings. So what is increasing the entropy of the surroundings? What does that mean? So heat is a physical manifestation of increasing the entropy of the surroundings. So when your battery gets hot, you are dumping entropy to the surroundings and heating up the battery. So let's think about this a little bit more detail. Let's define something called practical irreversibility. Now, of course, we can never do things thermodynamically reversible because that means we go infinitesimally slow, right? So we can never reach that limit, but we can approach it. And we'll call something practical reversibility. Let's rest this stuff up here. So we'll do a thought experiment. I have a spring. You guys can pull your springs and weights out if you want from your desk. So you're under your desks and you can set them up. So you put your spring on your desk and go ahead and put the weight on top. And the weight will push down on the spring, right? And the spring will push up on the weight, right? And at equilibrium, what will happen? Nothing, right? The forces will balance, right? So Kx equals mg. So this is the, K is the spring constant, X is the displacement of spring from equilibrium, M is the mass, G is the gravitational constant, right? So the forces balance, this is freshman physics. Now, this system can in principle do work, right? Because this spring is compressed, it's pushing up, right? So this spring, if I took this weight off, what would happen to the spring? It would shoot up, right? If I just slid the whole weight off all at once, would the spring do any work on the weight? Would it increase its gravitational energy? No. So if I just slid it off horizontally, right, the spring would just go fly up, no work done. Where would all the energy stored in that spring go? To the environment, right? The spring's going to fly up and it's going to oscillate back and forth, and eventually it's going to dampen, and it's just going to make heat. Now let's do the experiment a different way. Imagine that I took off the weights, I cut this block up into a bunch of small pieces. What would happen now if I took off one small piece? The spring would go up a little bit, and I have a little piece of mass right there, right? but this would go up a little bit. And then I took off another one, and then I took off another one, and another one, and another one. Am I doing work on the mass? Am I raising the kinetic energy, or no, sorry, the gravitational potential energy of the mass? Well, I'm going to slide them off horizontally, right? So every time this goes up, I'm going to slide them off at a slightly higher elevation. You guys see that?
Yes.
Yes, right? I'm lifting part of the mass up. The mass could then be pushed over the cliff and fall down and, kill someone, right? So that's doing work. So what if I made the mass pieces infinitesimally small? That's purely thermodynamically reversible. If I made these infinitesimally small, I could take these off one little piece at a time and the spring would go up. I could put them on one little piece at a time and the spring would go down. No entropy loss, purely thermodynamically reversible system. So it's the same thing with electrochemistry, right? You do the reactions really slow, one electron at a time. You can do it thermodynamically or near thermodynamically reversible if the kinetics of the reaction are reasonably fast. If you want to do things at a very fast rate, you have a lot of irreversibility, you waste a lot of energy. This is the whole field of catalysis, is minimizing the generation of entropy. Let's link this to electrochemistry a little bit more explicitly. So what governs the thermodynamics of an electrochemical reaction? The Nernst equation, right? So can you tell me what the Nernst equation is? E equals P naught plus what? RT over NF, ln concentration of O over concentration of R, for example. So the Nernst equation, in everything we did in chapter 1, we used the Nernst equation is used to link electrode potential. This is the electrode potential, right? Link the electrode potential to solution concentrations. That's what the Nernst equation does. When does the Nernst equation hold? Does it always hold? Is this always going to define the electrode potential? Or if I have an electrode, can I always control the O and R concentrations at its surface based on applying a potential? In chapter 1, yes. And we assume the reaction was Nernstian. Not in general, no. So we have to think about it a little bit more in detail. So if we write the expression, so O plus n electrons going to R, we can write that with a forward and a reverse rate constant. Kf, K back, right? So for a Nernstian reaction, Kf and Kb are large. Put that in parentheses, because large is sort of a meaningless term unless you have a comparison, right? But we'll talk about that in chapter 3. We'll talk about large compared to what. It basically needs to be large so that we call the exchange current densities are comparable to the current we are trying to pass through the cell. In reaction, Kf and Kb are large, so that Nernst equation always applies at electrode surface. And we call this reversible. So this is, by definition, a Nernstian reaction is a reversible reaction. Okay? So if it's Nernstian, it's reversible, it means the Nernst equation always applies. The Nernst equation is simply a manifestation of thermodynamics, of free energy. If thermodynamics governs everything, it's done in a reversible limit. But if the reaction is done fast, then it will be done non-reversibly, right? And that means that these concentrations may not be at the electrode surface what the electrode potential thinks they should be. Or another way to say that is you're sweeping the potential, and these concentrations can't respond fast enough by passing electrons back and forth because these rate constants are too slow. And so we'll go through that in chapter 3 in some detail. Okay, we're going to end with one last thought experiment. So let's take a reaction. Zinc plus 2AgCl plus goes to zinc 2 plus 2Ag plus 2Cl1. Okay, so there's a reaction. So let's do a thought experiment. How would I measure delta H for this? How could you measure delta H? If you were like, if I asked you a question, like you do calorimetry, right? Okay, so you mix in calorimeter. Standard, you have to do under standard conditions, and you make sure, this is kind of practically difficult, to make sure extent of reaction small, so that you don't use very much of this stuff up, so you don't really change the concentrations and stuff. And then you can basically find delta H naught equals negative 233 kilojoules per mole. Okay, now let's say we do the same thing, but now you're going to construct a cell. Does everybody understand what I said here by make sure the extent of the reaction is small and you have standard conditions? 1 molar, 1 atmosphere, those sorts of things. And if, as the reaction progresses, like you use up all of one of the components, you're not measuring delta H naught anymore, right? It's delta H under some other concept. So let's say you construct a cell, and you have zinc, and you have a resistor here. So resistor, and you have silver over here with some silver chloride on it, and you have some zinc chloride in solution, right? I have a cell, and I place the whole cell in a calorimeter, and I let this thing discharge. Am I going to measure the same heat release as here? Again, I'm going to let it discharge, but only a small amount. Everything's going to be in standard conditions. Same thing here, but now I just do it in an electrochemical cell, and I make the current run through a resistor. Am I going to measure the same thing as here? Something different, and doesn't depend on R. What do you think? The magnitude of the resistance. So the way to think about this, the way I like to think about it is at the end of the day, you're making the same thing, right? In one case, the excess energy is released as heat just because you're recombining these two species, you're reacting these two species, the excess free energy from that delta G of reaction just is released as heat, the enthalpy part is released as heat, right? And here, we're doing the same exact reaction. The chemical reaction is exactly the same. The mechanism is a little different. We're now running the reactions through a resistor, and we're pulling some fraction of the free energy out to run the current through this resistor. But the net thermodynamics has to be the same. You will still, the total heat release will still be delta H naught equals negative 233 kilojoules per mole. Okay, so you guys see that? I mean, you have the same products, the same chemical reaction, the pathway is different, but delta H naught can't depend on the pathway, right? But of course, I used some of the free energy I had here to do something in that resistor, to drive electrons through that resistor, but that just generated heat too. Okay, so now I can get a little clever, right? I can take my wires, and I can take them, and I can make part of the cell, I can put this part in one calorimeter, and this part in another calorimeter. So now I can do, this is C, 2 calorimeters. Now, what am I going to measure where? This is where it gets interesting. We'll call this QR, right? And QC. So the chemical and, or I don't know what R and C actually stand for.
Resistor and the calorimeter.
Calorimeter and the resistor. Excellent. I like it. We'll go with it. Okay? So what's going to be QC plus QR? What's that equal to? Better be,
Ideally, it would be delta H.
it better be the same, right? Negative 233 kilojoules per mole. Okay, but what do you think happens as the resistance goes up and I make the reaction go slower and slower and slower? You think I'm going to pull more work out through the resistor or less work out through the resistor? So one way to think about this is it takes some free energy to make these reactions in here go, and the faster they go, the more free energy you need to lose to drive it, so the less they'll be available to do work in the resistor. So it turns out, as R goes up, the magnitude of QC goes down, right? So as you increase R, QC goes down until you reach a limit when R gets infinitely large, right? And we get to the reversible limit. And as R goes up, QR goes up. I'm using more of the free energy of this reaction to drive current through the resistor by making the resistor larger, by making the current go slower, or lower and lower and lower in magnitude. So in the limit of R goes to infinity, you have QC equals 43 kilojoules per mole, QR equals 190 kilojoules per mole. Okay, so here, this is the work that I can actually do. This is the free energy. So delta S, let's do this quickly, equals Q reversible over T in the system. So this is the delta change in entropy of the system is going to be the reversible work divided by T. And T delta S naught equals the limit of QC as R goes to infinity. And that equals negative 43 kilojoules per mole. The heat generated in the calorimeter is purely due to the entropy, the fundamental entropy required for this reaction to go forward. You can't get that. That work cannot, that energy cannot be used for anything, right? It has to happen, like, you know, delta, right? Delta G equals H minus TS, right? Or alternatively, H equals G plus TS, right? So if I measure H total, there's two components. There's an entropic component and a free energy component. The free energy component is available to do electrical work. That's what we measure. That's why delta G equals negative NFE, not delta H equals negative NFE, or delta S equals negative NFE. G is the free energy. It's the amount that can do work, and that's what you measure with the cell potential. And for any finite R, you cannot quite get the full delta.